So here we go. How do we decide how the atom connected to the benzene ring affects the electrophilic aromatic substitution? What we're about to walk through is kind of frowned on in some circumstances because what we're using to describe the reactivity isn't a mechanistic aspect because we're looking at resonance before any reaction happens. Officially, what we should be doing is what we did in that last activity. We should be looking at the intermediates that are formed and how those intermediates affect the end result. Okay? But we can kind of cheat a little bit, and we can use resonance to our advantage to help us predict something about that reactivity. Okay, so we've got three examples here. Benzene is going to be our 0 point. Okay, that means it's right in the middle. Okay, it's our baseline. So if we make a substitution on that structure, we're going to replace one of the hydrogens, and we're either going to replace that hydrogen with an atom X up top or an atom X down below. But the thing to note here is the second part of this. It isn't just that it's an atom X. In the bottom case, it's a positive atom X. And in the top case, it has a lone pair of electrons. So it's effectively a negative atom X. Okay? That positive and negative gets a little bit wonky. So really what we're addressing there is partially positive, partially negative. The formal positive and the formal negative allow us to use resonance structures to really dig into this and draw them out. Okay? And so that's why I'm pushing it to the extreme, and we're going to the formally charged structure as opposed to partial charges. So let's play it out and see what happens. If I'm going to start with the top, because why not, the electrons could come down, which would then cause an exceeding of the octet at the carbon of our benzene ring. So that's okay because we have another pi bond that we can move. So what we're going to do is take this pi bond and we're going to move it. One of the common things that I see students do is go, okay, well, I'm going to move it. And they're going to start moving bond to bond. It's not that that's wrong, but then that causes another problem. And another problem. And another problem. Which then shuttles everything right back. And they go, well, there's no resonance. There's no resonance because you're making a flaw in your argument. Okay? When we move electrons, the electrons can move from atom to bond, or bond to bond, or bond to atom. And if you're trying to find as many resonance structures as possible, don't go bond to bond because you're shortcutting that atom and you're losing access to that information. So if we now draw the result out, I'm not going to show all the hydrogens. The other pi bonds didn't move, but we now have a negative charge on that carbon. Atom X is, yes, going to carry a positive, okay, but that isn't a big deal to worry about. What's important is that we see that negative charge and where that negative charge is located. Okay, so it's two big pieces of information we got to look for. So why is it important that it's negative? Well, remember in the EAS reaction, the aromatic ring is effectively the aggressor. It's the one donating the electrons. To donate electrons, we have to have electrons. A negative is a perfect symbol of having electrons. So if we look at that, that structure shows electron density at the ortho position, which would suggest the ortho position could react with an electrophile. Right? For those of you saying, but there's resonance, and we'll see that show up at the other positions also. Well, it's a good thing we know how to draw resonance. Whoops, because we will go through and test that. And what you might have noticed is I started to draw the pi bond. I actually don't want to move the pi bond, okay, for a couple reasons. One, it's not going to work as a valid move, and it will die very quickly. But perhaps more important than moving the pi bond is that when we're looking at resonance, we need to move the most active electrons. The most active electrons here are not the neutral pi bond, but the negatively charged lone pair formal charge up here. We exceed the octet, we'll again move the electrons, and the result that we would get is a new resonance structure. And this is where you go, aha, now we're going to have that meta have electron density. Well, if we follow where the electrons fell, The meta never picked up electron density. I get electrons at the para position. And if we continue to play this game around the structure, what we will find is that I never build negative charge at the meta position. I only build it at the ortho and para positions. For those of you saying that you could draw a Lewis structure for your benzene, okay, by putting a negative charge. So we drew out that kind of purple one, long, nasty arrow. Couldn't we have done this? Okay, well, yes, we absolutely could have done this. And really what you're addressing at that point is the intermediate analysis, and that's okay. Right? But the other reason why that particular resonance structure is not going to be of really any value is thinking back to what we were trying to see. We're trying to evaluate how the substitution of atom X on the ring affects the benzene. You just picked a random pi bond to do resonance. Right? It's not that that doesn't happen, it's that why? That's not showing how atom X affects the reaction. Your focus should be on where that difference is, which is atom X. Draw resonance from atom X. Okay? So if we kind of summarize what we've got in red so far. In red, we had atom X with electrons. Okay? And when we had atom X with electrons, we noted that the ortho, and I'm actually going to flip this, that the para and the ortho positions were activated. Okay? And we're using the word activated because they have electrons at them. Okay? There's that lone pair. Okay? So that's what atom X is doing. It is directing the substitution to happen at the para and ortho positions, and it is activated. As we talked about in the last video, the ortho is mildly sterically hindered, right? Which is why we should list para then ortho as far as our reactivity. You will often hear people refer to it as ortho-para because ortho-para alphabetically makes more sense and it sounds nicer. It sounds nicer because we want to hear that alphabet. Right? If we say para-ortho, everyone goes, oh my God, that's stupid. Why would you say that? Because it shows the clear delineation between para's preference over ortho. So break people's brains, say para-ortho directing. Okay? So what happens if atom X, instead of having electrons, had a positive charge? Okay? And this is again where, oh, it just does the same thing. Well, yes and no. Go through and look at it. Okay? With that positive charge, what it's going to do is take the electrons in that pi bond and draw them outwards. Okay? You'll also note that there is no need for a second arrow. That is it. All you need is one arrow. Draw only what you need and no more. That's going to leave a positive charge at the ortho position. So this is interesting. Now we are deficient. Oh, that was not a good word to try and spell. Fudge. Close enough. Deficient in electrons at the ortho position. Right? So if we were looking at the reactivity, I would not predict the ortho to react if atom X had a positive charge because I'm putting a positive charge at the ortho position. If we continue to move around the ring with our resonance, we'll note that that positive charge now kind of shuttles around the ring. Right? And we end up seeing deficient at the para position. And if we continue, we'll see deficient back at the ortho position again. Okay? What does this mean for us? And we could continue to draw that back around so we get the positive charge back to the beginning. Okay? So first and foremost, do we expect the ortho and para positions to react? Well, no. Remember, the benzene ring must act as a nucleophile, an electron donor. These don't have electrons to react at those positions. Those are not likely to occur. Okay? So if the para and ortho don't happen, well, then that must mean the meta does. Okay? Because it's the only thing left over. Is it activated though? So in this case, X we'll call it without electrons. The meta is the only position without a positive, so it at least has some electrons, but it's not formally negative. Okay? And if anything, the ring overall is carrying a positive charge. Well, I needed the ring to be negative to act as a nucleophile. If it's positive, it's less active, aka deactivated. So if I see an atom X that is missing those electrons, I would predict the substitution to happen at the meta position, and I would expect that reaction to happen at a very slow rate because the ring is literally missing the electrons it needs to run the reaction. So it would be deactivated. Okay? If we think back, Friedel-Crafts required an activated ring. Ta-da! There's the language. Okay? The language is referencing what we see in red. Okay? And that's kind of the big summary that we're getting out of this. What we're looking at is how those resonance structures interplay with each other to align so that we can see this. Okay? And we can see it nicely drawn out here. If atom X has more electrons than hydrogen, and this becomes the weird one, okay? Remember, it's all based off of hydrogen. So if we have more electrons than hydrogen, we would predict it to be an activator, whatever atom X was. Okay? And that means when we look at our substitution, we would get ortho and para directing. If atom X had less electrons than a hydrogen atom, we would expect it to be a deactivator and meta directing. Okay? The more electrons than hydrogen is probably relatively straightforward for most of you considering this. And that's because, well, hydrogen has a whopping how many electrons? Not zero, because I bet you said zero. Hydrogen doesn't have 0 electrons. Hydrogen ion has 0 electrons. A hydrogen atom has 1. Okay? So when we're looking at this, we're looking at any atom that has more electrons than 1. Wouldn't that be everything? Doesn't everything have more electrons than hydrogen? What if it was a positively charged atom? By definition, it has less electrons than hydrogen because hydrogen is neutral. If I'm becoming positive, I have less electrons than that. Right? That's just has to be what it is. Right? The variance between that becomes challenging. Your textbook has nice slides on it or nice images of it. To be honest, I don't know that I have that image in the slideshow. It's definitely not in this video. It might be in another one. Okay? But what we need to do is look at that atom X, the very first atom that is connected to the ring, because that's the other thing. You could have all sorts of junk way out there. See, way out there, you have no idea what's going on over here. There could be some weird, scandalous thing on the wall. You'd have no clue. Has to be right next to it for it to have any meaning whatsoever. Okay? So, let's pick a couple quick examples. Let's clear some of that red text away. Draw it out, nice equal purple. Activator, deactivator. Okay? Where would I expect the reaction to occur? Ortho-para, or para-ortho, or meta? See, I'm still doing the ortho-para stuff. Okay? And most people look at it and go, well, nitrogen has more electrons than hydrogen. It is therefore an activator. I like that logic. That's some pretty solid logic. Some pretty solid logic until you actually draw out the Lewis structure. And when you draw out the Lewis structure, what do you find? That nitrogen is electron deficient. Right? It is formally positive. And in fact, the nitro group is so electron withdrawing, it doesn't matter even if it withdraws a pair of electrons out to make that new, of course there's text underneath there, to make that double bond, because when it does so, the nitrogen stays positive. Okay? It would still not be under its valence for charge, and it would stay positive. So the nitro will be a wickedly strong electron withdrawing group. So it is a deactivator. Okay? Let's try another one. Right? Well, atom X in this case is a carbon. We don't see anything weird, resonance-wise. We could be like, well, we got fooled on that whole Lewis structure thing, so let's go ahead and draw those out. So we could draw out the hydrogen and be like, well, there's nothing really tricky there. It's just carbon. And well, does carbon have more electrons than hydrogen? Yeah, that's why it's lower on the periodic table, because it has more electrons. Carbon is an activator. Right? It is not a super strong activator, because if we look back at our example, we were saying we had a lone pair to donate in. We're not formally donating electrons into the structure with this carbon. Right? All it is doing is partially donating. It's through what's known as an inductive effect, which I know could be confusing for other things. Right? The electrons are moving through the sigma bonds, and so it's not a formal motion of electrons. It's just kind of a weak, I'll give you a few cents to help out, but I'm not going to give you, $20, right? What happens if we switch this up and we now put fluorines? Well, it's still carbon. Shouldn't that still be electron donating? Well, except that those fluorines are more electronegative than the carbon, and all three of them withdraw electrons from the carbon, making the carbon partially positive. Okay? Since it is partially positive, that becomes an electron withdrawing group, and we're looking at, as I drop my pen, we're looking at a deactivator, and we would expect meta direction. Okay, let's try one more example with a carbon. We'll do two. Still an activator. Okay. While there is an electronegative element at there, it's at least one bond away. It may not be as activating as just a straight up methyl, but it's still going to be activating. What happens if I bring that carbonyl right next to it? Okay. Well, now, through the power of resonance, we can even see that we're dropping a positive charge on the atom next to the ring. That is very clearly a deactivator. Right? And so these are the big kind of things that you should be looking at. Look at that atom immediately connected to the ring and start to immediately categorize it. It has more electrons than hydrogen, activating. It has less electrons than hydrogen, deactivating. And then associate the terms deactivator or deactivating with meta and activating with para-ortho. Okay? Last example, and it's a doozy. Chlorine, or really any halogen. And yes, I'm being a bit of a jerk here by throwing on those lone pairs. Okay? Chlorine does have 3 lone pairs, so it shouldn't be that big of a deal. Should this be activating or deactivating? Well, it's clearly activating because it has lone pair electrons. But it's clearly deactivating because the chlorine is more electronegative than the carbon. Well, which is it? Don't we have to pick one? Sort of. Remember, in all of our systems, what we're doing is coming up with these kind of comparisons. And within those comparisons, we have a line. That line splits the difference between those, and guess where our chlorine and our halogens fall? Right on that line. What do I mean? If we were to go through and look at our halogens, halogens have more electrons than hydrogen, so we would expect this directing or electron donating ability. Right? And if they were donating, we would expect it to be an activating group, and we would expect para-ortho substitution. Okay? But they are not willing to share those electrons. Because they are not willing to share those electrons, they are meta-directing and deactivators. Activator, or activating, if we use the same verb conjugation. Okay, well, then which is it? Right? Not everything works the way we would want it to. Of course, I drew this. Oh, man, just pretend you aren't seeing me do any of this activating, switching around, because it, of course, makes sense to have it written this way. Okay. What are our halogens? They are para-ortho-directing, but deactivating. Okay? They split the difference. They are the line. So our halogens, based off of their electronegativity and their general unwillingness to share electrons with that carbon, deactivate the ring. However, because they do have those electrons kind of sort of align within the structure, and I'll draw something that sort of, or at least some people will show, and that starts to shuttle the electrons towards the para and ortho positions. Okay, what am I talking about for that drawing? If we were to draw a Hayworth, which is everybody's favorite, I know, we have the p orbitals of our benzene ring, and we've got our chlorine out here with its lone pairs. Those lone pairs are in sp3 atoms, but they are darn close to aligning with the pi system. Okay? That alignment is an increase in stability, and that's where that para-ortho directing effect comes in, is that chlorine can kind of help to stabilize some of those intermediate structures, and that's why we see that para-ortho directing effect and the deactivating effect all at the same time, which I know isn't the most lovely conclusion, but believe it or not, that is my conclusion. So with that, thanks for listening. We'll talk soon.